Hi, everyone. I'm Ollie. So you might have seen this logo. That's me. And I work for Cosmian. So we take security research, multi-party computation and homomorphic crypto, and put it into products that actually protect your privacy. So yeah, trying to do cool stuff there. Anyway, you're here for Constable, so stop talking about me. Why Constable? Well, I guess everybody has used Constable somewhere, maybe for an array length or something. So usually you use Constable to save resources. You want to make sure that something happens at compile time instead of at runtime. So you just especially if you're embedded, you don't have many resources at all, so you don't really want to use them up. Other things that you can do is you can reduce some type system trickery. Sometimes you end up working around weird things. So you're working with the system to get it to do, the type system, get something to do that you want to do, but it's very hard to do, so you're doing weird tricks, and it just gets annoying. So Constable saves you from that because it just allows you to write stuff in real Rust code, so it can do whatever you were previously doing in complex ways. Also, you can prove constraints at compile time, so you can make your program secure by ensuring that some things are simply checked at compile time, error out at compile time. And most importantly, because we can. That's my reason. So there's a bunch of levels of constant evaluation that you can get at. So there's the omnipotent level. You know it is from scripting languages. You have an eval function. You can just eval anything, and you get a result from it. And you can just use that at compile time and then use the value suddenly during compilation. So that's omnipotent, in crazy levels, because you can do anything in there. You can open network connections and connect to whatever database somewhere and then do weird stuff on the internet. That's not what you should do in Constable, but you could. Then there's restricted omnipotent, which is well, you're not allowed to do network to the internet because that's kind of weird. So let's not do that. And then there's inherently limited, which is basically a glorified calculator and allows you just to compute some values, and that's it. And so we are right now at the very restricted omnipotent. So big shout out to Scott Olson, who wrote the so-called Miri interpreter, which is the base thing that we're using in Constable in rustc. It is basically all-powerful. It is a virtual machine interpreting Rust code. It is a virtual machine in all of the definition of a virtual machine. You can run anything in there, theoretically. And we want to go to restricted omnipotent. So we want to keep some restrictions around. We don't want anything to be possible at compile time, and there's a bunch of reasons for that. So first of all, soundness. If you allow anything at compile time, you get some weird issues where you compute a value over there and you compute it over there, and it's suddenly not the same value, even though the logic is entirely the same. This happens, for example, if you have random number generators. As at compile time, that's a bad idea. Then again, that all boils down basically to determinism. You want your constants to always be the same thing. So if you have a constant and you look at it, and you look at it later again, it should still be the same constant. And finally, for us implementing constant evaluators, we don't want this to get more complex than it is. It's already 8,000 lines of code inside a Rust compiler. That's pretty big for just a constant evaluator, but we'll get to that later. So we want some restrictions. For example, we don't want mutation of global state. Mutation of global state essentially boils down to random number generators, because you can have some global variable and you're mutating, you're accessing def random or something, getting random numbers, whatnot. Mutating global state is a bad idea because you get the initialization order problem that you know from other languages. So yeah, no global state. We don't want any non-determinism, so you're not allowed to check the bytes from some pointers, because pointers to some things in memory, they change the address between compilations, and the order is not defined, the actual addresses are not defined. So we don't really want that kind of things. And we also don't want SIMD, again, back because it's very complex to implement thousands and thousands of SIMD instructions. So there's some restrictions that we just want to keep around, and we have to work around those. But we have loads of unnecessary restrictions. So one thing I often get is why can't I have vec new? I mean, vec new doesn't even allocate. It doesn't do anything. It's just creates a vector that has no elements. So Why can't I have this? Well, there's some problems with that, because internally it uses things that are a little bit more complex than doing nothing, and those little bit more complex things, they aren't really possible right now. So, but we're working on that. There's an open RC for that. Then another thing is box new, vec push, so anything that kind of like needs to heap. So we want heap during const evaluation. I'll get to that later and explain in detail how that is happening, because it's actually a very hot topic, because C++ just got heap during Constable for 2020. So, but yeah. So loops and if conditions, so any kind of branching, we can't do right now, and we want to get rid of them. And cool update, yesterday morning a new pull request was opened that actually will help us get there, and another one is in the works, so I'm pretty positive we can have this in the next month. Well, very unstably, and not for anybody using it unstable, but like it'll work at least. Then calling trait methods. You cannot call a trait method in Constable right now. We have constfn since the 2018 edition, so you can define your own constfns, but you cannot call trait methods. There's no way to specify those bounds. So there's an open RC for that, and yeah, once we have that, then we can implement it, and then we'll have that. So this is work in progress, but we're getting there. Format is basically culmination of everything that you saw above. So we need trait methods, we need if, we need loop, and we need heap allocations. And then you will be able to call format. And when you can call format, you can basically like end up using like all of 30, because that just uses the same stuff. So my goal is personally to get 30 at compile time. So you take like a configuration file, like a TOML file on your source, and then you run it through 30 at compile time, and you get struct at compile time with all your configuration, and you get an error at compile time telling you that the file was bad, instead of like getting it during runtime and having your product crash somewhere. So the last restriction that is basically unnecessary is that we're not really allowing you to do unsafe right now. You can do unsafe, but only if the unsafe contains nothing that is actually unsafe. So I'll get to unsafe later. Unsafe is pretty cool during Constable, and yeah, I have some examples what we're going to do there. But everybody here probably came here not to hear what you can't do. You want to hear what's going to happen, how it's going to happen, and so let's continue. Things that like aren't Constable, but well, they are now. So strulen just got Constable like yesterday. It's not merged yet, but like it's working. And str is empty, and all these kinds of functions. So stuff in the standard library is getting Constable all the time. Basically, if you want something to be Constable, just open an issue about it, and like we'll fix it. Like most of the things can be Constable nowadays, so constfn. So we can just do that. So panic is constfn. It's pretty useless because you don't have if, so it's just gonna panic at Constable time, which is an error, but like hey, it works. You can have let mut, so you can actually like write some pretty linear code, and you can have destructuring in there. So you can create things and destructure them again, and so on. So that works. And there's all kinds of functions on your triplet integers that are constfn now. So you have like overflowing and wrapping operations, like what's it? Count zeros, count ones, whatever. Like there's loads of operations on integers that are now constfn, and you can use them. And there's probably more that we could make constfn. So if there's something that you're missing, just well, open an issue about it. If you're telling us about it, then we can probably fix it. But most importantly, what probably a lot of people really want is pointer offset from. You might ask, why do you want that? Have you heard of offset off? It's like to calculate the offset of a field in a struct to the base of the struct. So you may wonder why you need that. Well, it is used in so many kinds of abstractions where you're doing some neat hackery at compile time. And this feature is constfn now, and we can use it again. Unnightly, obviously, but like it works. So these are kind of things like library-wise that we get. But there's more than that. You can basically end up making anything constfn. Like literally, you point at it and we can make it constfn. There's very few things that we can't. I gave you the restrictions earlier. Everything outside these restrictions, make it constfn. Tell us about it. If you want it, we'll make it constfn. So what kind of stuff is happening as constfns now? I already told you about loop and if. There's accepted RCs for that. So this is just like implementation work, and it's happening right now. So there's some open RFCs, which give us like calling trait methods and vec new and so on. And this is going to happen sometime soonish, I guess. We don't have an RFC yet for heap allocations. Once we have the RFC through for trait methods, then we'll go to the heap allocations. And with heap allocations, people can start doing all kinds of crazy things. You can start allocating graphs at compile time and just putting them in a static, and you have them available later. And the computation is like all happening at compile time. Or perfect hash maps. Well, you compute a perfect hash map at compile time. Right now, this is all like procedural macros and all kinds of other dark magic. But then you can just run your normal code that you would run at runtime, just run it at compile time, put it in a static, and you're done. And of course, I already talked about unsafe shenanigans. And there's loads of unsafe shenanigans, so they're super, super fun. But before we go into all of these details, let's give an example about heap allocations. Because heap allocations, especially in the presence of C++ getting in 2020, are a very hot topic. So heap allocations have loads of curious problems. Most of them boil down to this. You have a constant, and that constant is of type string. However you get that constant, I don't care. Like you somehow compute a constant, and then you use that constant. You say let x equals foo, and then at some point x is being dropped. You run out of scope, you drop it explicitly, whatever. The question is, what happens at this assignment, let x equals foo? Usually, when we didn't have heap allocations, that was always a very simple solution. We just bit copy the constant into x, and then we have the value right there. But if we bit copy the constant string object, we are referring to a static heap allocation. This is like in static memory. This is in your data section somewhere where you can't get it back out. You can't deallocate it. It was never allocated. This just exists like a static. It would be like calling free on a static as like undefined behavior. So this is illegal code. We can't have this. So the question is, what kind of things are OK and what kind of things are not OK? And this is what we were able to take a lot of information out of the C++ discussions about heap allocations. In C++, this is illegal. You're not even allowed to compile the const definition. So the const foo string is just not legal. And we are not going to make it legal either because it has this obvious problem here. So what kind of things are OK? So as I showed you, the first thing is bad. But if you put that thing behind a reference, suddenly it's OK, because you can't move out of a reference in Rust. So anything behind a reference, even if there's heap allocations in there, is basically fine. You can just access this and you can't move out of it. You need to clone it. And once you clone it, you create a new heap allocation, and everything is fine. There's no problems there. And even if you convert this to a str, it's no problem, because then it's just a str. It doesn't even show you that there's a heap allocation there, and you can't move out of it anyway. And any kind of other non-heap types, so if you have integers or custom structs or so that don't have heap in there, you can just put them directly in a constant, and everything stays fine. So this kind of setting where something behind a reference is OK and something not behind a reference is maybe problematic, maybe it reminds you of anything. Like, it took us like 2 weeks to figure this out when we were like sitting there and just discussing the whole time about all of this heap stuff. And at some point, somebody noticed, well, it's almost like send and sync. It's like not quite send and sync, but like we could create 2 new traits. One is const safe, which means you're allowed to put it in a constant. And the other thing is const ref safe, which means if it's behind a reference, then you could put it in a constant. So the idea is we'll create the system, and we'll just do an unsafe impl const ref safe for string, because we'll say, we checked the implementation of string, and we are very, very sure you're allowed to put it behind a reference. Because once it's behind a reference, the only thing you can do is clone it, or turn it into str and just like work with the slice. But like you can't do anything more than that. So we have a system forward here, and now comes the difference to C++. We are allowed to put heap allocations into constants, as long as they're protected somehow behind references or something else. And in C++, they decided it's too dangerous. We can't do this because we can't possibly ever check that this will work out. So the only time you can use heap allocations in C++ is during your compilation, but the final product does not have any heap pointers. Even if you convert it to an %str, if you do the same thing in C++, if it's a char pointer that came somehow from a heap allocation, you're not allowed to do that. It's just forbidden. But in Rust, we can do this because we have our awesome type system that has stuff like send and sync that we can now reuse for this kind of setting. So we'll be able to do a lot more, and we can do it safely. We can do it completely safely, as that the user will never have to worry about it. If it compiles, it's fine to do. And here's the example which will make all of this possible. If it's const ref safe, this is the T-bound const ref safe here, then you can make it const safe if you put it behind a reference. So everything is being done for you. You as a user will never actually have to touch this. This is all happening in the standard library. We'll expose it like send and sync. So if you're doing your own shenanigans, you can just implement the appropriate unsafe traits, and you'll be fine. And so yeah, we have a system now to get heap allocations there. And this system, it doesn't look very complex. It isn't very complex. And we are pretty positive we can get this through maybe in the next year, that at least you have it on nightly. And so we're not playing catch up to C++ here anymore. We're like on the racetrack, just taking over. Not having taken over yet, but like we're there. OK, so heap allocations. Now we're coming to unsafe. Unsafe is awesome because unsafe gives you compile time, undefined behavior. It's the best thing. I love it. So undefined behavior isn't really that problematic at compile time because you just get an error. But sometimes you don't get an error because we are not like, we haven't solved the halting problem yet, so you can't really figure out if it is really undefined behavior. So what we're doing is like we reserve the right, if you do undefined behavior, we'll just break your code in the future. But by breaking code, I mean like we'll emit an error later. So don't do undefined behavior. It's not a good idea. For example, what is undefined behavior? Well, if you have a Boolean, let's take the y first. You have a Boolean, and you transmute a 3 to a Boolean. A Boolean's memory representation is only allowed to be either 0 or 1. If it's a 3, that's undefined behavior. Because a bool with a 3 in there is just an illegal value. It makes no sense. Or if you cast an integer to a raw pointer and then dereference that, at runtime, that may be OK if you're like on embedded and you're giving like the address of some hardware thingy. But at compile time, like, what is on the address 42? Like, what am I supposed to do as a compiler developer? It's like there's nothing there. So these kind of things are undefined behavior. There's loads more about like, well, all kinds of undefined behavior that you already know. But like, if you do any of these things, they will likely give you a compile time error telling you exactly why you screwed up. So you can actually use this a little bit to play around with undefined behavior to see like the boundaries of what Constable can do. And there's lots of fun things to do there. So there's other things that are not undefined behavior, but like you still need unsafe for. For example, here we create a reference to the number 42. We convert that to a raw pointer and put that in a constant. And then from another constant, we dereference that raw pointer. And this operation is basically the same operation we had in the previous slide, where we were dereferencing a pointer that was actually just an integer address. But here, it's an actual address. It's an address to the number 42 somewhere in the stack, not in the stack, in a static memory. And we can dereference that totally fine. So the dereference operation is something we really want at compile time because people will be able to do these nice shenanigans. So do UB or not UB? That is the question. And the problem is, there are much stricter rules at compile time because we just really can't figure out what you're doing here. Like if you put this pineapple variable above pizza, stuff will happen that's not good. So for example, we're doing the same thing we did earlier. We take an address to a statically allocated 42, convert it to a raw pointer, convert it to a usize, and then we divide that usize by 99. But like, what does that do? Like, we don't have addresses at compile time. There's no memory. Like, what is dividing like magical address of something by 99? Like, we don't know. Like, okay, we could add like symbolic executors and all kind of set solvers and whatnot and go crazy, but like, do we really want that? Like, this is probably not a good idea anyway. So, and I'm not talking about a pineapple of pizza. I like that. So, sometimes we have less stricter rules at compile time too. So we don't have any concrete rules about the alignment at compile time. You can just do weird alignment things. So if you have like an array of U8 bytes and you convert that to a U64, like an array of just U8s can be anywhere in your memory. It doesn't have to be aligned. It definitely has not to be aligned like a U64 needs to be aligned. And if you do this code at runtime, that's undefined behavior. If you do this at compile time, it'll compile. But we reserve the right to break your code in the future because you're doing undefined behavior. So there are very careful rules what you can actually do. And you can do more things. Like you can do undefined behavior at compile time when we might not catch it. But it gives you the right to do all these kinds of cool things if you're just as careful as you should be at runtime. Hello? So, summarizing, we don't really have any limits, but we are restricting ourselves on purpose just to stay sane, because at some point, like, we don't want to put all this complexity on users, because that's what Rust is all about, taking away the complexity, making it saner for everyone to work with code, and we want to do the same thing for Constable. And there's loads of work happening right now to make everything easier for you, so you don't have to write any complex trickeries to get stuff to work at compile time. So you just write normal Rust code and just execute the same thing at runtime at compile time, and you'll be all happy. Many features that somebody might want need a like small base features. So there's lots of work that's happening where it's like we're implementing 3 base features just to get 1 major feature. So for example, as I said, for 30, we'll need like heap allocations, we need if, we need loop, we need traits, so there's even 4, so yeah. And what we actually need is more people telling us what they want to do at compile time, as like so we can prioritize. There's so many things we can do, but like there's very few issues opened actually about people wanting something to be const-defend. So that's my call to you. Open more issues telling us to do stuff at const-eval time. Yeah, so this is basically everything I had prepared, but I have a small appendix because people were telling me over the last few days all kinds of stuff that they're already interested in. So I prepared a few small things. This one is a compiler flag. You can add this flag to a compiler, and it will simply take off the guardrails. Like, it'll just be like, OK, sorry, I'll stop trying to be sound. I try to run everything that you give me. And you can do loops in there. You can do if. You can do random other stuff. And it's a very bad idea. We're using it just for internal testing. Never use this in production. Never, ever. Some of the tests that we have actually panic actually, because you're doing something unsound that the compiler just doesn't understand. So yeah, don't try this at home. But if you want to play around with the Const evaluator and see how far it can go, use it. I want to shout out to the static assertions crate. If you want to check something at compile time, use the static assertions crate. It basically does this weird trick in some other way. So if you want to check if a Boolean is true and error out otherwise at compile time, what you do is you create an array of 1 element. You convert the Boolean to a usize, and then you index into the 1 element array. If the Boolean is 0, you get something. If your Boolean is not 0, you panic. And panicking at the compile time error. Wonderful. So we have static assertions. Use it. It'll get better error messages and so on once we are developing more things at in the compiler. But I've been told that it's going to go 1.0 soonish, the static assertions crate. So you can use it, and it won't change its API. We're just improving the diagnostics that you're getting. So you can just use it everywhere. And now a final small anecdote. So you can compute the Fibonacci sequence at compile time unstable, but you'll get a compile time error too. And the compile time error will tell you the Fibonacci number that's being computed. So this program uses while loops. It uses if conditions and so on. So yeah, you don't really want to use that. But what it's doing, it's computing the length at the Fibonacci number and using it as the length of the type of the underscore variable here, and then assigning an array of the length 42. So you'll get a type mismatch error. Before that, you get an unimplemented expression type. That's the error that's actually going to error out. But we also get the mismatch type error. And there you can see it correctly computed a 144 for you. And then it errored out and died. So yeah, so that's it from me for today. If you have any questions, just grab me at the rest of the day, and I'll also be here for the Impl Days tomorrow. 2 days ago, somebody had a problem they wanted to fix in the Const evaluator. The PR is open now, so just come to me. We can usually do this very quickly, because many things I just don't know about don't work, and they often can be fixed pretty quickly. So yeah, thanks for being here, and